Okay, been asked to help out with the interpretation of what our analysis revealed as we went through this system where we were going to pull up our bear sensitive things and get it out of the reach of the bear in our camp. Right, tree over here, tree there, and we're pulling down on the rope to pull it up. Okay, so now what we found out was that it was this cable right here that broke first at a weight of about 107 pounds. And so you come back and you say, all right, well, what was the difference between original guess and the statics-based answer? Right? So in our original guess, all we did was look at a very simplistic free body diagram here. We assumed that this big long cable was the one that would break first. And the breaking first idea is, well, let's put this weightless thing here and then we'll start adding force to it, pour sand into it, increase the weight. Well, which one of these three breaks? And it turns out to be AC, and that will happen at the 107 pounds, right? And so what happened there was that this big long rope contributed a lot of additional downward force at pulley A, right, in that free body diagram. So we had both of these, and we had this one we're pulling down. Interesting question becomes, what happens if that's not 30 degrees, but what if it's 90 degrees? Or what if it even swings up so that the segment AD is actually going upwards, which pragmatically is not going to be very useful unless you're climbing the tree and pulling up to do that. Right? All kinds of interesting things that will change our answer about what happens. Certainly this angle had some sort of contribution to our model, right? And of course we also assumed that it was this DAE cable that was the limiting factor, turned out to not to be. So that was a big, huge influence about why the model predicts a different behavior. Now, if we go and experimentally try to confirm our results, we do it and we conduct an actual test, and the weight that something fails at is not the 107 pounds, but somehow maybe 80% of that, about 80 and 82 or something, I don't know, pounds. Then what's going on here? Is it, of course, a manufacturer's fault in the rope? What's going on here? So let's list some of the sources of the real behavior, particularly how that differs or compares to our theory. I'm going really fast, so that's one reason why my spelling absolutely stinks here. Alright, so some of these maybe are just brainstorming, but we're going to get into some of the realistic factors that people don't tend to think about. One, of course, is that the geometry of our model is not real, so the angles are not the same. That could certainly contribute to that. So what would be then the case? What are some of the angles that might change that have an influence? Well, at 30 degrees, if it's not 30 degrees, if it's something else, is it smaller, bigger? What might make it break earlier? That's something I want you to think about in more careful detail. Right? Certainly, damage to the ropes, maybe from prior use, would certainly mean the strength isn't what we were predicting, and so that could have a factor. We have not included friction in our model. What would that really do? Well, it certainly will increase the tension in DAE, and since we're a little bit sensitive to what that tensile force is in DAE, that could do some things. I don't know if it's the major thing, but here's a particularly major important one, and that's the natural variability of the rope strength. So here, I don't know if it'll certainly change the real world compared to our theory. Now, which way it goes, meaning do we get a larger, not smaller one, we'll have to sort of probe into that. So if we look at and test a whole bunch of these ropes, all in maybe the same condition, maybe fresh out of the box, really fresh out of a plastic bag, and you then aggregate all that data, you're going to find that it's going to have some sort of bell-like curve in its distribution of strength. And you're going to also find that the average strength from testing is going to be somewhere in here, but the rated strength on the package is going to be less than the average. That's by design of the manufacturer and their tolerance for liability. If they say that the rope has an average strength of 300 pounds, they know some joker is going to go do something that's going to put a lot more force on that. And even though they might be right, they know what the American legal environment is like. So they're going to tell you probably that the rating is 200 pounds instead of being maybe 300 pounds. What the spread of this distribution is, that's called variance, or standard deviation is essentially the same thing. And where they decide to report it compared to an average is their choice. There's no requirement there, at least in a product. Now, for things like structural steel, this is a little bit differently done, but certainly a manufacturer selling the customer a rope can choose what this ratio is, or what this distance is, all that kind of stuff. Right? So that's a big contribution. Now note, if they rate it at 200, but a big percentage of this is all the way up higher, that would not be a strong indicator of what we observed here, other than, well, what if it was the rare event that we were way down in here? It doesn't, just because the rope actually had only 180 pounds of strength instead of the rated 200 doesn't mean that the manufacturer has a flaw and that they're at fault. Probabilistically, out of every 1,000 ropes, you're going to get something down in here, right? And you take the probability statistics class to find more out about how to estimate what that likelihood is. So it could be one of the causes. Maybe it's going to be this angle that's not the same. That might be the bigger thing, because we're probably not holding that right at 30 degrees. Now, how much we vary that could be a lot. We're taking cosines and sines of that angle. In one of those, that might be real sensitive. The other maybe not. You have to do additional exploration on that to figure out what percentage change here has any significant effect, say 20% change on the predicted weight associated with capacity. A whole lot of really neat probability statistics things to go through on that.